Thank you, guys. So let me start by thanking the people that are actually up here speaking and whatnot this year. This is an incredibly good conference, amazing good content. So from a sponsor perspective, you know, we really think this is one of the best conferences we could possibly participate in. So from a Mellanox perspective, right, we're a high performance interconnect technology provider for both InfiniBand and Ethernet. And I'm not going to really spend all my time with AI here. It'll kind of cross HPC and the boundaries of AI. And what's interesting is as I start this conversation, right, is we see that you know, in the world of HPC and big data and artificial intelligence and in particular deep learning, right, they really do share the underlying hardware needs. And for the most part, the same software needs are also you know, very particular to the segments of data. And so throughout the whole conference, right, we've heard numerous times about big data. We live in a world of data, how we're using this data, and how RDMA plays an important role, regardless if you're taking a look at it from an end-to-end kind of how is data ingest being thought about and being executed from an enterprise class scale, or if it has to do with deep learning, and then how HPC and AI come together to find new solutions in some of the new real-world workloads, such as renewable energy and solar power and these types of things. So from a Mellanox perspective, we not only and this slide is actually indicative of both HPC and AI. And what's really interesting is that the largest systems in the world today, and I think it was even called out yesterday, that more than 75% of the HPC installations actually have key elements of AI and distributed AI computing, right? And so that is, of course, inclusive of Oak Ridge and Lawrence Livermore, which are standing up their new IBM Power-based machine, Summit and Sierra. But Mellanox also powers you know, the fastest supercomputer in Japan, as well as in Canada, right, for the University of Toronto, and also based on a new capability, a new topology. It's not new, but it's much improved from a Mellanox implementation called Dragonfly. But as well in geosciences and other numerous supercomputers out there, Mellanox is really the de facto standard, not only for HPC, which we're actually, you know, probably best known in years past as being the top interconnect provider for HPC, but as well now, once again, for machine learning and in particular deep learning. So, you know, some of the products and elements that we offer from an end-to-end perspective are both Ethernet and InfiniBand, 100 gig, and soon to be introduced here as the quantum-based and ConnectX-6 for HDR. Then that's 200 gigabits a second. So we have a complete end-to-end solution. And inclusive of that is a new product called Bluefield, which is a system on a chip. I won't go into that in detail here in this presentation, but suffice it to say, it couples the power of ARM processors and integrated ConnectX-5 with all of our advanced core offload capabilities and acceleration to provide a very powerful SoC for building things that are very useful across HPC and AI, such as JBOFs and JBOGs. So that's going to be a very interesting technology to watch as it's being introduced into the industry now. So really, right, exponential data growth everywhere. This is nothing new. I'm not going to spend any amount of time on this slide, but you know, no matter what source that you talk to, most everyone agrees that year over year, right, we double the amount of data being generated. And you know, we invited some key speakers this year to this conference, in particular Slack, right? So they were here yesterday. There's an incredible amount of data that will be explosive in just in the next few years. We'll have more data than we could possibly even compute on it. We'll be throwing away more data than we'll ever actually be able to even store. And when I say big data, I mean really big data, right? So the average automobile is able, the autonomous AV type technology today for AV, these fleet vehicles are actually generating up to 40 terabytes of data today, right? And you multiply that by a fleet of vehicles, and that's just an amazing amount of data. But if you take a look at the aerospace and the manufacturing space, this example of this aircraft engine, right? So for a 12-hour flight time for this one engine, right? We're able to actually now produce 844 terabytes of data just in this single jet engine. And so how do you move that data, and how do you analyze that data, and what do you keep, and what is real? And these are the types of issues, right, that companies are deploying that are dealing with this every day, have to determine what do you keep, what do you work on, what do you parse out, and how do you lake it, and all this type of stuff. But from an interconnect perspective, the one thing I think that is most important, and one of the reasons why I love to work for Mellanox, right, is we live in this world of data. What could possibly be more critical to your design decision than the interconnect? Moving that data, getting it from point A to point B or to point C in the least amount of time in a most highly optimized fashion has to be one of the first design choices, right, on people's minds who are designing and deploying for HPC and AI. So I won't cover all of these, but I will dig into some detail of really what's important to AI and machine learning as well as HPC from an interconnect perspective, and that's really the fundamentals of RDMA, which of course you've heard from nearly every speaker in the last day and today. RDMA is very key in unlocking native performance because, right, you bypass the OS and you bypass unnecessary data copies and this type of thing, and so it's always been very understood by the high-performance computing industry that RDMA is paramount of importance, right? To remove from the CPU and give the CPU cycles to your application so your application can scale and deliver the performance that you're expecting, right? Throwing more compute resources at a problem, you should expect better scalability. So GPUDirect RDMA and async I'll touch on, and then I'm going to touch on Sharp, which is a capability that's useful in HPC today as well as AI. But for all of these reasons, right, you need the highest bandwidth and the lowest latency interconnect, especially when you're talking about deep learning and artificial intelligence. All right, so from Mellanox's perspective in our direction, it is really about removing from the CPU, right, and the CPU's involvement in any of the communication tasks. And that's not just from the stack perspective and native to the operating system and how it's handled, but as well from the algorithms and whatnot that are actually implemented within the core element of how HPC works and how AI works. In particular, with collective communications and these types of things, we're able to now perform data operations within the switch fabric, right? So we can actually manipulate data and work on the data as it traverses the network. So we fundamentally are turning the network into a coprocessor, and by doing so, we're introducing an amazing amount of performance benefits to the existing workloads today. If you were doing everything on TCP, or some sort of legacy type interconnect, right? You can expect that Sharp's going to give you 10x performance hands down from even just the traditional way that you would implement over TCP, but that's above and beyond the implementation around RDMA, right? So we're really enhancing the ability of the network to become a first-class processing element. Being able to handle MPI collective or MPI operations within the network itself, especially from a network perspective, we can do MPI tag matching in hardware, so no longer needing to have to do software implementations. Shield is a mechanism to be able to do very fast recovery of anything that potentially could break in your network. Let's say a cable that gets unplugged or something of that nature. And then of course GPUDirect RDMA, and so. Those are the core elements that I'm going to cover today, not Shield in particular, but from an HPC perspective, let's say we take pure elements or pure HPC codes for weather and automotive and chemistry and these types of things, right? The numbers that we publish are often the numbers that our customers are giving us to publish, right? So it's not just Mellanox saying, hey, we get nearly 2x better performance on WRF, right? We have a key customer that has versions of WRF that have come to us and said, wow, we took it out of the box and we couldn't get performance over this other interconnect, and we put your stuff in Mellanox and we get 1.9x better performance. This is amazing. And so, you know, I think for HPC and AI, right, RDMA and the core capabilities of Mellanox's direction of moving more processing into the network is the way of the future, and it's going to be the definite approach to exascale. So from an AI perspective, one of the key things that I like to talk about are the frameworks, right? So we have a lot of people here I know that have now installed. Last year I came up and said, who has installed TensorFlow? And I think I had 2 hands. And if I ask that today, has anyone installed TensorFlow or Caffe, or who's playing with the code, I get a few more hands when I go off and talk to people. People are starting to actually dig into it, and they're starting to understand the value of RDMA when it comes to scalable distributed training. In other words, you know, a lot of people have installed TensorFlow on your laptop, and you may have done it over a single server, but as you distribute across many multiple servers, throwing more resources at a problem, RDMA is paramount right now for all of the frameworks, and that's inclusive of TensorFlow, Paddle, Microsoft's Cognitive Toolkit, Caffe, all of these. They're all now out of the box, or at least out of the GitHub, ready to take advantage of RDMA. And that's also inclusive of many of the supporting libraries, including NVIDIA, right, which has their DGX box. And you know, they've built a world-class computer called Saturn V that takes advantage of their architecture, as well as the InfiniBand architecture, and an optimized library called Nickel, which is NVIDIA's collective communication library, are all natively supporting today RDMA and GPUDirect out of the box. So I think DK probably covered this in day one, right? GPUDirect is the ability to move data. I don't know what happened there. GPUDirect is the ability to move data from one GPU into a remote host GPU, right? Just by means of the network. You don't need to have the CPU involved. And this really dramatically reduces latency. You can get about 10x performance just by making sure that the GPU and the InfiniBand card sit on the same root complex, and you can move data directly from one GPU to another GPU without having the CPU involved. And that frees up the CPU to actually now manage and execute all of those CUDA threads that are being launched to run your AI. The next class of GPUDirect is async. And async not only offloads the data plane, but it offloads the control plane, so that the CPU is now no longer involved in having to just monitor the CUDA threads that have been launched, right? And so the network is giving more control over to the GPU, and with that, you're going to get not only additional performance with some of the core applications that we've benchmarked today, and a lot of them are stencil-based applications, but it also allows you the ability to use lower cost, cheaper CPUs, because you don't need such a powerful CPU to go in and manage, you know, all of this CUDA threads. Basically, the CUDA will launch batches of threads to the CPU, and then we give over network control. And this is going to be the next generation of GPUDirect, right, which will allow you to build more powerful, more cost-effective AI nodes. So a little bit about some of the elements of distributed training and getting into the capabilities of what we call SHARP. So distributed training, of course, can take a very, very long time. And you know, Uber has said this, and this is one of the challenges that people are trying to overcome, and that is really getting out of the box. Getting out of the box of, you know, heavily densely populated GPUs into a more distributed model, similar to a Beowulf implementation of HPC, where you have many servers of GPUs all working on the same problem in hopefully a better scalable way. And so when you work on these large training sets, it can take actually weeks. And the goal is to really reduce that amount of time, because really the data scientist it's really about satisfying the data scientist being able to, at the end of the day, kick off a training job and come in the morning and be able to then review the results and understand how the model actually works. or in many cases, training needs to happen frequently. And in some cases, as we just heard, sometimes you don't need to retrain data. But in a lot of cases, when you're involved in deep learning in the model development cycle and tuning of your model, right, training happens actually quite frequently. And so weeks then turns into months, and months turns into a very long time when it comes to bringing something to market. So real life cases may require training regularly. Autonomous vehicles are one good example of that. There's so many interesting scenarios when it comes to deploying an autonomous vehicle that people may not have thought about that pop up every single day. Maybe you're driving behind a bus, and on the side of the bus is a picture of a big truck from some automotive or some movie, and there's a big picture of a truck on the side of a bus that's going down the road. But then in the back of the window of the bus, you can actually see what may be classified as a pedestrian. So the automotive industry is struggling with identifying all of the corner cases that you might possibly think about, and being able to create a very robust model or models, right, to deploy as autonomous vehicles are the promise of this generation. So basically, how do we solve for parallelism? Data parallelism is basically the solution, but how do we do that? And basically, as Alex described in Uber's presentation, right? It's basically you can split up the data into several mini type batches and continue to work on the data. And then there's always this notion of having a parameter server involved to be able to pass through the parameters and update the model replicas as you're scaling out your model. So from a data parallelism perspective, the communications here become very critical because of the workers to parameter servers are involved, and the servers to workers. And the communications may be frequent. They may be very, very high bandwidth. They may be bursty because of the different types of data. And then, of course, there's point-to-point collectives that are involved in being able to distribute training. And so RDMA really does bring in the element to be able to improve point-to-point collective operations. And in specific to AI and deep learning in particular, right, is Allreduce, right? These algorithms spend a lot of time in Allreduce. It's a paramount kind of collective operation specific to AI. So from a model parallelism perspective, right, some cases, right, the models just won't fit. I mean, GPUs are great today. They come in all different flavors of 8 and 12 and 16 gigabytes of memory on a GPU. There's other implementations and methods of training as well, FPGAs, different ASICs and custom ASICs and this type of thing. And so maybe the model is not going to be able to actually fit into the device. And so really model parallelism is the answer there. And because of high bandwidth and low latency requirements for model parallelism, along with RDMA, it's actually mandatory almost when you start moving into from data parallelism environment to a model parallelism, where the network really becomes a critical element. So a little bit about SHARP. SHARP is really addressing these challenges for both data parallelism as well as the model parallelism paradigm. SHARP is basically this aggregation and reduction protocol, and it is really it's applicable today to HPC in the sense that it's very tuned and optimized on our current generation of switch IB products with EDR, right, to be able to perform data aggregation and collective operations to be managed within the switch. Giving better performance and removing the need for a centralized CPU-driven kind of data aggregation. So the switch does it. So from an HPC or from an AI perspective, different from HPC is that AI is, of course, bound to larger messages. And these messages can be actually done on the HDR quantum-based 200 gigabit switches at wire speed up to 2 gigabytes of data in size, right? So that's significant because you're not only reducing the amount of data on the wire, right, but you're also removing that external resource or that parameter server that you may be using completely away. So just taking a look at from a performance advantages of taking Sharp into consideration of doing things on the switch as opposed to how you would do it in software shows a very flat latency curve, right? As you move out in cluster size with more numbers of nodes. You really want to keep a very low latency curve as you add more compute resources to it, right? That's really the goal. And with a software implementation, you can see the increase in latency. And so that's really the goal of Mellanox, right, is to remove latency, to make things very predictable performance. The more nodes and the more resources that you add to it, you want to be able to have a very predictive outcome, right? So doing it through software is one way to do it. It's the way it's always been done, but now we can manage these type of operations from within the switch. And you can see that 75% reduction in latency, even out to 128 nodes, is something that's going to be very critical to exascale and to large-scale distributed AI. So basically, this is kind of an animation or pictorial of Sharp in action, where you could think of a parameter server being up here. The different compute elements are here with the GPUs and your servers, and basically you fundamentally can deliver your results to a parameter server, and the data aggregation is done within the parameter server. But with the quantum-based switch, or with an EDR switch IB 100 gig switch that has Sharp technology supported, you can actually remove the need to have that external parameter server. So now you're not only removing the need for CPU cycles to be able to handle the data aggregation, you're also removing the need for any kind of external parameter server. And so if the server's handling all of your gradient averaging and providing all of the model replicas with the synchronization to be able to create a more accurate model as you scale out, then you can do that all in the network. Then that really adds value to the network and to your infrastructure, because it really is about maximizing the performance of the GPU. That really is what all of this translates to, right? You have these GPUs. They're not cheap. They're fairly expensive, even though they're saving you a lot when it comes to how many servers they are replacing. Nevertheless, you know, they're about a $7,000 to $9,000 a pop kind of expense, and if you put 8 of them in a box, you really want to maximize your total investment that you did, and there's no better way to do that than with Mellanox Fabric, and that's hands down why Mellanox is enjoying the success of today, because we can actually just show out-of-the-box performance. This is out-of-the-box TensorFlow performance, right? 50% better performance by taking TensorFlow from the get, and with the contributions and the optimizations that's been done to include native RDMA, you're going to get much better scalability. And if you take a look at the yellow line here, right, that's basically a GPU times 32 GPUs, and then we plot that on the line. That's perfect performance, perfect scalability. And if you take a look at TCP, right, your speed up and over the amount of GPUs just doesn't compare to the ideal performance that you're going to get. And basically what that translates to, right, is improved accuracy. So you're going to achieve more accuracy in a reduced amount of time by taking advantage of RDMA than if you were ever to do it over TCP. Now, we spend a lot of cycles, a lot of engineering efforts in tuning and optimizing the particular frameworks. And I mentioned, right, our RDMA is supported out of the box, but TensorFlow is one that we do particularly focus on. This is work that we're doing with which it shouldn't be really coined as advanced verbs, but what we'll talk about, they're the same verbs that we're using, they're just more optimized for TensorFlow. And you can see that as you, so first of all, we get 6.5x performance out of the box, right? And this is with TensorFlow 1.65, I think, is in the repo. And so all of this will be contributed back upstream to the TensorFlow Git. Even with the larger models, and this is VGG16, right? So this is with the larger models. You're going to get about a 6.5x performance improvement over that of 10 gigabit running also with RDMA. So this is comparing a 10 gig, and a lot of people say, hey, 10 gigabit Ethernet or 10 gigabit in RDMA is probably good enough. We had the kind of early discussion, like how many GPUs to how many gigabits of network do you think is probably appropriate? And I think NVIDIA may tell you it's 2 to 1, 2 GPUs for a 100 gigabit network, and Uber may have their 25 gig for a GPU. But one thing's for certain, 10 gig is not enough. And if you're running 10 gig right now, and this is the same model that you're training, and you're getting 335 images here, right? You're not squeezing out the performance of that $9,000 GPU as if you were running 100 gig, leveraging RDMA and our offload capabilities, right? So this slide says, yeah, we're not only tweaking and tuning and being able to squeeze out the best performance with TensorFlow, but it really also screams 10 gig isn't enough. Okay, so I talked briefly about Nickel. Nickel is NVIDIA's optimized communication library that also takes advantage of RDMA and GPUDirect, actually. So NVIDIA is a great partner, and of course they have the lion's share of how you do it, and they are the who's who in AI, right? So they're a great partner of Mellanox, and I think that they recognize that InfiniBand and the importance of the network is actually critical to the performance of how they're delivering with not only their DGX solution, but how they deliver that to the OEM designs as well. So regardless if you take advantage of distributed TensorFlow and if you use Nickel or you use MPI or whatnot, you're hands down going to get the best performance out of the box with Mellanox. So hopefully I did that in more than enough time. I kind of rushed through it because I never know if I'm going to ever have enough time. I didn't encourage questions while I was talking, but now I'm going to encourage all kinds of questions. And for every good question, you're going to get a cookie. They're out in the front lobby. But you have a question? Go ahead.
With Sharp, you can put, like, as you said, functionality within the switch, right? How
right.
do you deploy this functionality? And I'm biased and I work for Docker, so maybe containers and solution there.
So Sharp today is enabled with a it is an open implementation. So you could design for Sharp today. It's mostly implemented through MPI today. So HPCX is an offering from Mellanox. It's our MPI. It's based on OpenMPI, but anything that is MPI based is probably the most effective way for HPC to take advantage of Sharp. But there's a lower level programming reference as to how you would take advantage of Sharp from a much lower level, from a Verbs type implementation. And so to take advantage of building your own type algorithms to bring them to the switch is always possible, and we can certainly work with you if you have a specific need. Now, as well, when I say that, I mentioned the Bluefield device, and the Bluefield being ARM coupled with ConnectX-5. And so another way to extend functionality and capability from a network perspective is to kind of bring your own algorithms and be able to program them or implement them from a Bluefield device, right?
If I want to have logic on the switch, like a program that's running within the switch that is custom to me, then that's not possible as of today, I guess, right? Because
It will be very, very possible and very practical from Bluefield's perspective. But today, from a switch perspective, it's somewhat right now limited. It's not limited, but it's exposed through MPI. So we're able to manage and execute MPI operations from within the switch. Is the first implementation of Sharp, which is what we have today. HDR comes out in just a couple months, and that, like I said, is able to handle much larger messages, up to 2 gigabytes at wire speed for data aggregation. But it also opens up the world of opportunity for mixing and matching with Bluefield or with any of our other ASICs to be able to create a very highly tuned, optimized solution for your problem set. Because we often talk about AI and machine learning as something that's very general. And there's nothing general about it. Everything is unique. Everything has its own custom implementation, almost. Unless you're, doing handwritten characters or minced, or that's pretty well understood. But any other questions?
So you have any specific vertical implementation, like autonomous car or oil and gas? Any specific implementation of this deep learning you can?
Oh, as examples? Yeah, I mean, so one of the best examples, I think, are, I often just kind of refer to the Saturn cluster that NVIDIA has stood up. Right, so Saturn has been enabled with Pascal, and it now is sitting at NVIDIA with the Volta class GPUs, and so as far as specific use cases, right, Saturn is used across a number of scientific disciplines, and in particular, they do a lot with cancer moonshot, and they do a lot with media and entertainment, and they do a lot with AV, right? And so that's probably a flagship example, but what's coming online now with the #1 supercomputers in the world, right? Summit and Sierra. These are not only the largest HPC systems that are being built today, they're also the largest systems out there for AI. And in a lot of cases, if you take a look at the amount of flops in Summit as to how it's relate to AI, what I call AI flops or tensor flops, you're getting pretty close to exascale right there, right? As far as floating point operations per second. So that's a great example already. But that's something that's very interesting is the hardware is very similar underneath for HPC and AI. And we see that more and more as even in the geosciences space, right? The work that they're doing there, which didn't used to be that would overlay very nicely onto a GPU because it was limited to 8 gigabytes in size. Right now we have GPUs that are up to 16 in gigabytes and more. Even the workloads in the geosciences space are very much flagship examples of Mellanox in the power of RDMA and being able to move data from GPU to GPU or FPGA to FPGA. But I'm not going to say that who's using AI today, because it'd be easier to find a case of who probably can't use AI. Much similar to who was that who was saying about taking this red spray paint and we spray it on everything? Maybe it doesn't work there, but for the most part, AI is very applicable in financial services and genomics and automotive and geosciences and just you name it. So I am out of time. Yeah? But if you have any more questions, you can always find me at the break or send me an email. We can always take it offline if we don't connect up here. But thank you for your time. And Sydney, who's up now? Thank you, guys.